other topics I could cover. Thus far we've been talking about essentially the solar system. So one may raise the question that, well, even if you can interpret various features of the universe described in the fifth canto as corresponding to certain features of the solar system as understood in modern terms, still, what about the universe as a whole? Because the Brahmanda described in the fifth canto is supposed to be the entire universe, and yet according to modern science, the universe as a whole is utterly enormous. It extends out for it's like 20 billion light years or so if you go out to the quasars. So what can one say about that? So there's a chapter in the book here, chapter 7, in which I discuss modern cosmology. So I thought I would go over that. So as to give you an idea of the kind of foundation which modern cosmological thinking has. Now, in this chapter, I only discuss one particular aspect of modern cosmological theory, although it is an important aspect. But there are many other things that could also be discussed. So what I'm talking about there is the idea of the expanding universe. So probably everyone has heard of this concept that the universe is expanding. This is connected today with the Big Bang theory of the universe. According to this idea, at a certain point in time, which would be about 20 billion years ago, 15 or 20, it varies, depending on the different estimates, all of the matter within the universe was compressed literally into a point, and it exploded. What this means, in effect, is that there was a mathematical singularity at the beginning of the formation of the universe. Because when everything is compressed into a literal point, then all the mathematics breaks down. The laws of physics are no longer meaningful. So in mathematics, that's called a singularity. So the idea is that somehow or other, beginning with a singularity, everything expanded out. And initially, as the expansion began, the universe was in the form of a superheated plasma of subatomic particles with a temperature of billions and billions of degrees. And it then expanded, and as it expanded, it cooled. And as it gradually cooled off, different forms of particle combinations now became stable because the temperature was low enough for them to form. And so at a certain point, protons and neutrons and so on formed, and then they began to form helium nuclei. Gradually, when the universe cooled off sufficiently, electrons were able to combine with these nuclei to form atoms. So you finally have a expanding cloud of atoms, which are mostly hydrogen and helium, almost exclusively hydrogen and helium, according to this idea. And the expansion continues, and somehow or other, these masses of atoms coalesce into clumps, which later form galaxies.
Somehow or other?
Somehow or other, because that's a great mystery. No one has yet even come up with an even partially adequate theory of how that is supposed to happen. It's a real problem because the expansion tends to drive things apart, and yet gravity has to be able to take over and pull them together into clumps. And all of the models people have tried to make for this thus far have failed. In any case, somehow it's supposed to happen. So galaxies form initially as clouds of gas. Then within the galaxies, due to contraction under the influence of gravitation, these clouds of gas coalesce into stars. So you have millions upon millions of stars forming within the galaxies. And then planets form around the stars, and this Earth is one such planet. And then life forms on the Earth, and so on. This is the story that they present. So one key ingredient in this whole picture is the idea that the universe is expanding. Now, when they say that the universe is expanding, they specifically mean that it's expanding in the manner of an explosion. So you might ask, well, how does an explosion expand? Well, if you think about an explosion, you'll see that, let's say 1 second after the explosion, one object may be, let's say, 100 feet from the center of the explosion, and another object may be 200 feet. Well, the object that's 200 feet away is going twice as fast as the object that's 100 feet away, because it's gotten twice as far. So, in an explosion, the rate at which an object is moving away from the center is proportional to how far away from the center it is. That's the basic rule. So, it is claimed, on the basis of observation, that the galaxies in outer space are moving apart from one another at a rate which is proportional to how far away they are from one another. From our own point of view, that means all the galaxies we see out there, on the average, are rushing away from us. Among nearby galaxies, there are some exceptions to this. But on the whole, as you go out, the idea is that they're all rushing away, and the further they are, the faster they're going. So this is related to a method for determining the distances of galaxies. And according to this method, if you can measure how fast a galaxy is moving away from us, then you can tell how far away it is, because the speed is proportional to the distance. So that's the basic picture of the expanding universe. The Big Bang Theory is based on this, because if it's true that the universe is expanding as though it were an explosion, then you can argue, well, maybe it really is an explosion. And in that case, at some point in time, it would have been compressed into a small volume from which it exploded. So that's how the argument goes. Yeah?
I hate to harp on this point, but the universe as a whole is expanding according to modern idea, but there's still these localized areas of contraction within the general expansion that are stars and galaxies and whatnot.
Right. That's what they'll propose.
With no explanation as yet.
They cannot explain as yet how those contracted regions got started. You see, once you have local contracted regions, then you can see why they should remain stable, because gravity keeps them clumped together, and then the clumps just continue moving apart from each other. But the problem is, imagine that you have, say, an elastic sheet, and you're stretching it. The elasticity represents the force of gravity that tends to pull things together. So you're stretching it. What would cause the elastic sheet to break into little clumps, which would then contract? Well, you might say, well, maybe it rips in certain ways. But you have to explain how it would rip in such a way as to form clumps of one basic size. If you actually take a sheet of elastic and do that, you may get it to break, but it'll probably tear in one place or something like that. The question is, how do you get it to tear into a whole series of roughly equal fragments evenly distributed across the whole elastic sheet?
The galaxies are more or less uniform in size?
More or less. There's considerable variation, but still, they're more or less. It's just like people.
Right.
There's a considerable range in size if you look at people, but still, there's a certain basic human size. So it's like that with galaxies.
Is their distribution in space more or less equal, or...
Well, people used to think that their distribution in space was pretty uniform, not perfectly uniform. For a long time, they've recognized that galaxies tend to form groups. But the idea, well, recent observations are tending to show that there is a whole hierarchy of sizes of clumps, and this is really hard for people to understand. There are clumps, and then there are clumps made of clumps, and clumps made of clumps of clumps. And in between these areas of clumps, there are what they call these voids, in which you don't find anything. This is what they claim. And this is hard for them to explain, why it should do that. So they have this basic idea of the expansion. Now, what we want to look into is what is the evidence for this? for this expansion. Yeah?
Is the Earth and the Sun and planets that are visible around here, are they moving away from each other right now? Measurements?
The idea is that the Earth and the planets in the solar system, they're bound together by gravity, so they're not moving away from one another. For that matter, the stars in one galaxy are bound together by gravity, so they're staying in a clump, but all the clumps are moving away.
How long do they move away for until they stop? Just forever?
Well, that's another area of speculation. There are basically two views on that. According to one view, the whole thing is expanding, but as it expands, it slows down. And at a certain point, it'll come to its furthest point and then reverse and start falling in on itself again. And then you'll have what they call the big crunch. So the Big Bang is followed by the big crunch. Yeah?
Didn't you say that the Vedas don't talk about gravity at all?
No. Gravity, of course, is another whole subject. They talk about gravity, and I'm going to say some things about it here also. The other theory that they have is that the expansion just goes on forever. According to that theory, our ultimate fate is that as the galaxies go expanding out, gradually all the suns will die out, they'll burn up their nuclear fuel, and be reduced to black, cold embers. And everything, all temperatures will gradually fall down to absolute zero. And all you will have will be a few, black rocks hurtling through the void forever.
Wow.
And this is the future. Yeah.
How is this big crunch theory? How does it? What does it do with the principle of entropy? Everything seems to be, when it all crunches back together again, it seems to have the same. It would no longer be random.
Yeah, there are great problems with the laws of thermodynamics when you apply them to the universe as a whole.
Yeah.
The whole idea of the second law of thermodynamics, entropy and so forth, practically you sort of have to restructure these laws when you talk about the universe as a whole. And there are different theories that people have. So that's another whole area of theoretical.
They just say that the specimens lie. They just say entropy doesn't apply in that case.
Well, yeah, there are. One idea is that the entropy does get reversed. You do go back to a state of greater order.
When it turns around, the direction of time shifts or something.
Not exactly that. There are different theories. You see, entropy is a very artificial concept anyway. Yeah. It's only introduced into physics by postulating very special initial conditions, because the laws of physics are time reversible. And entropy says you have entropy increase says you have irreversible processes. So how do you have irreversible processes if the basic laws are time reversible? So the way they get around that is by postulating very special initial conditions. So there are many topics to go into there. That gets very complicated, and it's really in the area of theory. So what I wanted to talk about was this question of, well, why do they think the universe is expanding anyway? What's the basis for that? Yeah.
How is a galaxy defined?
Well, it's basically defined on the basis of observation. Through telescopes, you see these little glowing patches in the sky. Initially, they were called nebulae, which means clouds. Now they're called galaxies. So they observe these and they speculate about what they are. So their present idea concerning what they are is that a galaxy is a huge cloud of stars and gas floating in a region in which you don't have so many stars and gas and as much gas. So that's what they think it is. Yeah?
Can the individual stars in the galaxy be resolved on present telescopes?
They can be in the Andromeda galaxy. That one is the closest galaxy to us, according to them. I think it's about 1.5 million light years away.
So at least for that one, they have direct sensual experience that it's composed of individual stars.
Right.
More or less like what we're supposed to be in now.
Yeah. you can see the stars there. I've seen photographs of the stars in Andromeda. It's a fact, though, that in most galaxies you can't resolve the stars. You just see a milky, cloudy kind of light. So I should point out, by the way, that you've probably seen pictures of what galaxies look like. Usually the picture you see most frequently is of what they call a spiral galaxy. It looks something like that. Sort of like a pinwheel. There are others, though. There are elliptical galaxies, which are basically either circular or elliptical, with just a sort of central mass of brilliance sort of fading off towards the edges. You will see descriptions to the effect that we are in a galaxy like this, and the sun is out on the edge of one of the spiral arms like that. The point should be made, though, that no one sees that with telescopes. What we actually see through telescopes is a band of stars in the sky. And that's actually, if you want to see what that's like, if you look in this, on page 60 and page 61, you can see the Milky Way as it actually looks in the sky. It's a bit dim on these pictures, but you can see it. In figure 11, you see this band here? That's the Milky Way. And in figure 12, it's a little bit hard to see, but I think it must be this band right here.
Yesterday was really good. I was there.
Yeah. So it's interesting, by the way, that according to Vedic literature, the Milky Way corresponds to the celestial Ganges. So that is described.
So it's a more concentrated area of stars.
Yeah, the Milky Way is a more concentrated area of stars. That's how it actually looks.
This is what the galaxies are they explained further in Vedic?
I'm not aware of any specific reference to galaxies in the Vedic literature, except for the Milky Way. But of course there, it's described as this band of stars, and it's identified with the celestial Ganges. But anyway, the question is, why do they think that the universe is expanding? So here's the history behind that. As I mentioned previously, there's a whole series of ideas as to how to measure distances of things. It's called the cosmic distance ladder, because you work your way up step by step. So when you get out to the area of galaxies, the basic theory they have is that among all galaxies of a given type, the brightest in a given group of these should have a fixed value of brightness. That's a theory.
Could you say that again?
Among all galaxies of a given type, say certain kinds of elliptical galaxies.
By their shape, you mean?
Yeah, classed according to their shape. If you look at a group of those, then the brightest one amongst in that group, let's say in space, in this region, there's a bunch of them. And there may be other things there, but there's a bunch of galaxies of a given type.
How do you know they're actually close to each other? Just because they're...
Well, just because they're in a group. You think, well...
As far as
you can't tell for sure. You see, this is how they reason. They'll say, well, it's probably that they're sure that they're all in a group because after all they're in one area of space.
Yeah, they could be, by distance from you.
Yeah, one could be close, another could be intermediate distance, and so on. So they'll say,
assuming that
you say the brightest one amongst them, on the average in such a clump, that should have a certain degree of brightness. Now, we then take the measured degree of brightness and we apply the inverse square law for diminution of light intensity, and on that basis we calculate the distance. That's an example of the way they calculate distances. It's pretty shaky. There's so many things.
I don't think I understand. Can you repeat that again?
Yeah, good reason.
Yeah. The idea, it's just like
they speculate how bright it actually is.
Yeah, they're speculating. What they want to do is get some sort of grasp on how bright the thing is.
But compared with what?
You see, the idea is this. It's a cosmic distance ladder. So suppose that applying this method, let's suppose you have some fairly nearby groups of galaxies. So this clump is nearby. And using another method that you have, you can tell how far.
Comparing it with a different method.
Yeah, you see, it's a ladder.
Comparing it with an already established distance.
Yes, it's a ladder. So
I see.
I'm just describing one step in the ladder.
Yeah, that's what I did.
Yeah, that's the key thing. So if you've already figured out the distance of this group, one way in which they do that is to use what they call Cepheid variable stars. There are stars that vary in brightness, and they argue that the rate at which they vary in brightness is related to how bright they are. So you can do a curve in which you have here a rate of variation, let's say. And here you have brightness.
You mean how individual stars will vary in brightness over a period of time?
Yeah, these stars have the property that they get brighter and then dimmer and brighter and dimmer in a cycle. And the rate at which they do that is related to how bright they are. This is their idea. By some curve, maybe it's like that. So according to this idea, if you look at a Cepheid variable star and you measure its rate of variation, say here, then you go up to the curve, you go over, and that tells you how bright it is.
Could you be a little reductionistic and say where that idea came from?
Well, we go.
I mean, you get one speculation from another speculation, but where's the...
It's the cosmic distance ladder. So there's many steps.
What's the first rung?
Well, the first rung, as I mentioned, was stellar parallax.
That one I could accept.
The second rung was statistical parallax, which I mentioned the other day. And there are a couple of rungs. I'd have to review it myself to see exactly what they are, but it
seems like each step is getting more and more speculative.
Yes, I think so. I mean, to be honest, actually, I studied some of this material before I became a devotee, and I thought it was doubtful then. See, then I was a true believer in all these things, but I thought it was doubtful back in those days. But in any case, yeah, what they do is, suppose you have a bunch of stars of this kind called Cepheid variables, and you have determined by some method how far away they are. Then you can measure their rate of variation, and from how far away they are and how bright they seem to be, you can figure out how bright they really are. And then in this way you plot this curve. And once you've got this curve, you say, let's assume this curve applies everywhere. And then you say, okay, here we've identified a Cepheid variable, and we've measured its rate of variation. So we look on this curve, that tells us how bright it is. So knowing that, we calculate how far away this is.
When you say how bright it is, like average brightness or something?
Well, yeah, because it varies, you'd measure it as being, say, the midline of the variation. You know, they have their definitions worked out as to how to handle this. So, that's the method using Cepheid variables. But then it turns out there's another kind of variable star, something Lyrae variables. They also vary in brightness, and that's related to how bright they are, but the relationship is different than the relation with Cepheid variables. So if you mistake one of these stars for a Cepheid variable and apply this curve, it will be the wrong curve. You'll get the wrong answer. So you have to be careful to determine what kind of variable star you're looking at. So there are many complexities in all of this. Yeah?
Is there a desire to know brightness in an attempt to understand the distance? Is that their ultimate?
Their aim is to find out how far away things are. The basic principle behind it is that as things move further away, they get dimmer. Yeah?
It seems as though they could calculate that if they had one object that they knew for sure how far it was and everything in relationship to that, they could judge how. But do they even have one object that they know for sure how far away it is?
Yeah, well, you see, you have two problems. One is you're not sure how far things are. The other is that objects can be of different intrinsic brightness. In other words, a searchlight at a vast distance, and that would seem just as bright as a flashlight from a much closer distance. And so all you can see is this little point of light. How do you know if it's a distant searchlight or a nearby flashlight? How can you tell? So this is the problem that they're facing. So yeah?
I'm just wondering, you know how they calculate like the size of the sun?
Yeah.
That's based on the distance away. So that's the whole thing, is finding the distance. But it seems like, you know...
Right. Well, they're trying to find the distance. And of course, the basic problem is that no one's been out there. So all we have is light coming down. And they use radio waves that are coming down also. So from looking at that light, you have to figure it all out. So that's difficult. But this is just the beginning of the story. So this is enough to give you the idea that you have some pretty speculative, shaky steps piled on top of one another in order to get an idea of how far away these galaxies are. But let's suppose you've done that. Now you know how far away they are. Now here's the next step. And this involves what's called the redshift. So the basic idea here is, you know, light is a wave. And it has wavelength and frequency. Light of longer wavelengths, it would be, say, like red light. As the wavelength gets shorter, it goes down the spectrum through yellow and green and so forth towards the blue end.
Roy G. Biv.
Pardon me?
Roy G. Biv.
Roy G. Biv?
Red, orange, yellow.
Oh, yeah. Okay. If the wavelength is really long, you get into infrared, and then you get to microwaves and radio. Going the other way, you get to ultraviolet and X-rays and gamma rays and so on. So, now, it turns out that if you have something emitting light, and it's moving towards you, then the light shifts in its wavelength towards the blue end of the spectrum. That is, the wavelength becomes less. Now, the same thing happens with sound, so this is often illustrated with sound. If you hear a, say, train going by, blowing its whistle, you'll hear this characteristic sound, which is high-pitched, and then as the train goes by, it drops in pitch. So it goes like that. So the idea is that the whistle is producing sound of a given frequency. As the train is going towards you, the waves are compressed because the train is moving ahead a little bit as it produces each wave, so they're closer together. So they're compressed and have a higher frequency, so it's a higher tone. Then as it goes away from you, it's the opposite effect, and it has a lower frequency. So this is called the Doppler effect. So this can be used with to measure speed of automobiles and so forth with radar and so on also. So some astronomers noted that the light from certain stars is shifted towards the red end of the spectrum. Now, I have to explain what is involved here. Light coming from, if you heat a gas, this is a little bit of a technical point. If you heat a gas of a particular element, and then look at the spectrum of that, that is, you take the light from that gas, put it through a prism, and that prism will divide it into light of different colors. If you do this with sunlight, you'll just get a full spectrum of light. If you do it with a particular element, such as sodium, if you have sodium gas, if you heat that in a tube, you'll see that it looks yellow. And you'll see, in fact, that particular bands of light are there in the yellow region of the spectrum. And that's characteristic of sodium. But because it's moving away, the wavelengths are shifted towards the red. So they say, they call that a redshift. They interpret it as due to the Doppler effect. And they interpret it as meaning that the object is moving away. And the greater the degree of shift, the greater the velocity with which it's moving. Yeah?
At what speed does this become noticeable? Presumably it's a lot bigger than with sound waves.
Yeah, it has to be bigger, but it depends on the sensitivity of your measuring apparatus. if something is moving away from you at velocities in the rate of miles per second or kilometers per second, it's easy enough to measure.
A few miles a second?
Yeah, a few miles a second, you could easily measure it.
But this is totally a relative picture, isn't it?
Yeah, I'm just describing the idea of measuring the speed with which something is moving along your line of sight based on this idea of the shift of the spectral lines of the light. Because the whole expanding universe idea depends on this. Apart from this, there's no basis for the idea of the expanding universe. So I'll explain why that is. So, given this basic idea, some people began to observe different galaxies. And they said, well, it seems that the further away a galaxy is, based on our method of measuring distances, the greater the degree of redshift in the light from that galaxy. There was a fellow named Hubble who originally came up with this idea. In the 1930s, he measured distances and redshifts of many galaxies. And he said, well, we see this proportionality, that the further away the galaxy is, the greater the redshift. So then he said, aha, the universe is expanding. And it's expanding in this manner of an explosion. This was his conclusion. So this was a revolutionary idea, because until then nobody had thought of such a concept. Yeah.
So this redshift idea is sort of like the last rung on the ladder of measuring distances. He compared this with previous.
Well, you see, he was using measurements he made of distance using these other techniques that I alluded to. And then he began observing the redshifts, and he said, well, there's a correlation. Now later people said, aha, there's this correlation. So therefore, if we want to measure the distance of something, it becomes very easy. We just measure the redshift, and we know this correlation between distance and redshift, so we can get the distance. And that's what they do. It's a very widespread method.
They don't bother with the other things anymore.
Well, for the really distant things, they don't. So,
is there any other way to account for the redshift other than its being moving away?
Well, that's what we're coming to. Now, according to standard physical theories, you're pretty limited in ways of explaining a redshift. For example, a very intense gravitational field will cause the light to shift towards the red. But this isn't a very good explanation, because an incredibly intense gravitational field, if the light of a galaxy is shifted towards the red, then that gravitational field has to apply to that whole galaxy. And no one has any idea how to make that theory work. So basically, the Doppler effect is their main idea, how to explain the redshift. Yeah?
Has the redshift been measured experimentally on a scale that people can manage, like putting out a flashlight on a
Oh yeah. On the earthly scale, it works.
Yeah,
it works. Yeah, that works. That's not a problem. So, this is their basic idea. Now, that's the build-up of the theory that they believe in. Now I can tell you what's wrong with it after that introduction. Now, I should point out that most astrophysicists and astronomers fully accept this theory at the present time. But there are some professional astronomers who have found quite a bit of evidence that completely goes against it. So, to give you an example, one of these people is a fellow named Halton Park, who, where he got that name, I don't know. But he's an astronomer who for many years worked at the Mount Palomar Observatory. But he began making a lot of rather disturbing observations. What he would do is observe, say, a galaxy and some other object, such as a quasar, next to the galaxy, and even connected to the galaxy by some luminous material. And unfortunately, the galaxy would have a redshift indicating that, say, it's a few million light years away, maybe 20 million or something like that. But the quasar would have a redshift indicating that it's billions of light years away, radically different distance. Now, so he said, well, this seems to create a bit of a problem. The immediate reply, of course, was that, well, the quasar is much further away than the galaxy, and they just happen to be in the same location in space. So
why don't they use the same argument with their theory?
Yeah.
Maybe across some galaxies, though.
Right. But they would make that argument here. But then Art would come back to them and say, well, what about this luminous bridge that connects them? And they would say, well, there just happens to be a luminous bridge there, maybe coming out from the galaxy, and it just happens to overlay the image of the quasar. So they're actually at vastly different distances. So then Art would say, well, I can give you 100 examples of this. Are you saying that this happens by chance over and over again, that they're just lined up on our line of sight in this way? So he's presented this kind of evidence. Basically, this would seem to indicate that you can have redshifts that are not related to cosmic distance, because if his argument is correct, both the quasar and the galaxy are at nearly the same distance, being physically linked, and yet they have completely different redshifts. So that creates a problem with the theory. So that's one example.
What was his conclusion then? Why would that be happening?
As to why? Well, to get an idea of what he eventually came up with, I'll give you another example of something he's pointed out. He'll point out that you can have a series of galaxies lined up on a straight line, and this line is really straight. I mean, they're almost on an exact straight line as closely as you can measure it. And they have successively increasing redshifts. And he'll give quite a number of examples of this phenomenon. So he'll say, well, how are we to explain that? And he proposes, well, it looks as though one galaxy is emitting another galaxy, which is in turn emitting another galaxy. Galaxies are shooting out galaxies, and when they first come out, they have a higher redshift. This is how he interprets it. Now, that would be bizarre, because if galaxies are clouds of gas and stars, then how does one galaxy emit another galaxy? How can one clump of stars and gas throw out another clump of stars and gas? And why would the redshifts be there? So, this would indicate, his interpretation would require some kind of radical revision of our ideas of galaxies. But worst is yet to come. I'll try and sum this up quickly. We're running out of time. So, these are some of the observations of Art. Then there's the fact that the Hubble's constant, the relation between redshift and expansion and distance, is called Hubble's constant. And Hubble's constant has varied incredibly over the years. It's had values ranging over...
Is that so constant?
Well, some people have called it Hubble's variable. Like once it was 550, and then once it was 55, and then once it was 260, and 75, and 130. It gets around quite a bit. But that's not the worst thing. One astronomer observed that if you measure Hubble's variable in a direction in which there are a lot of nearby galaxies, you'll get one value. And if you measure it in a direction in which there are not so many nearby galaxies, you get a different value. And this works consistently. In other words, the degree of redshift, as varying with distance, changes depending on whether or not there are nearby galaxies. So how do you account for that? Well, he proposed what he called the tired light theory. According to this idea, light gets tired out as it travels long distances, and it gets redder as it becomes tired. So according to this idea, the redshift is not due to the fact that the things are moving away, It's caused by the fact that the light gets tired as it goes across space. And then he argued that, well, if there are a lot of foreground galaxies, there must be a kind of particle associated with them which is floating in space. So there are more of those particles near areas where there are a lot of foreground galaxies. So the light from the distant galaxies goes through more of those particles on its way here, so it's reddened more. And that's why the Hubble's constant takes on a different value if you measure it through a cloud of foreground galaxies than it does if you measure it in another direction. So the whole thing has nothing to do with expansion of the universe or things moving away from us. It has to do with light changing its wavelength as it moves through space. So that's another whole theory. And if you one may say, well, we don't like his theory, but what can you say about his data? Namely that the expansion rate varies depending on whether they're foreground galaxies or not. But this isn't the worst thing. I think I've got 4 minutes to the worst thing. 3. The really interesting thing is that redshifts turn out to be quantized. This was observed by a man named Tift. I've talked to him, actually. He's an astronomer. For 20 years, he's been publishing papers on this in the Astrophysical Journal. And he told me on the phone that they publish his papers because nobody can find anything wrong with them, technically. But he said there's sort of a tacit agreement that nobody talks about them. It's sort of the barrier of silence technique. What he's observed is that redshifts from distant galaxies come in groups. Now, how to explain this? The basic idea is that the redshifts are multiples of a certain basic value of 72 in the units that they use. So that means you can have a redshift of 72 or close to that. It could be, 71, 73 or so. Or it could be 144 or, like 142, 147 or so. Or it could be, what's the next one? 6 and, like that. With some range around that. So these are all multiples of this basic unit. So he said, if you make these measurements, you find that the redshifts fall into groups like this that are multiples of this unit. Now,
just everywhere in the sky is the sound?
Everywhere. So he said, well now, what does this mean? Well, if things are moving away from us and their velocity of recession is what determines the redshift, because it's a Doppler effect, does that mean that things are moving away from us at multiples of these different speeds? That doesn't make sense. You'd expect a continuous variety of speeds of things moving away. Not that they were coming as clumps. And there are things even worse than that. This is the last point I'll just sandwich in.
Is that the tip shift?
Tip. If you look at two galaxies that are orbiting one another in space, you see if two galaxies are nearby, supposedly by gravity they must orbit around one another. So if you measure the redshift of these relative to one another, that is, you take the redshift from the first one and subtract it from the redshift of the second, that should tell you the relative velocity of those things as they're orbiting around. So if you look at a lot of pairs of orbiting galaxies, you should get a whole variety of relative velocities depending on where you catch them in their orbits. But those are also quantized.
Same quantum.
Same figure, 72.